Thank you. Thanks, everyone. It's my honor and pleasure to be here. It's a privilege to be in Sofia. I haven't been here since 2009, so it's great to be here again. I'm going to talk about generative AI for code and beyond. And because you're such a varied audience, what will help me a lot is if you ask questions. So please free to ask questions at any point. If I don't want to answer, I will tell you that I don't want to answer. But so we will do it in this spirit. All right, so in the coming decade, basically, all software will be written with the assistance of AI. And so if you're an engineer, a software engineer, or an engineering manager, there is an AI in your future. In fact, it's not just in your future, it's in your present. Tabnine today writes 1.2% of the world's code. So this is code that is being generated completely automatically for developers who write code in their IDE. Tabnine is serving more than 1.2 million developers worldwide. I did not check, but probably some of them are also in Bulgaria. And automating 30% of the code that they write just generates it automatically for them. And really what Tabnine is, or the way that this whole thing is going, is that in an organization, in any software organization actually, there is going to be an AI layer that is just the next step in evolution above the standard things that you know and love from organization, such as the source control and the continuous integration, continuous deployment loop. There's going to be just another layer on top of that, an AI layer that learns from all this passive information that is stored for years and years of all your changes, all your commits, all the stuff that you've done in your source code that really captures the knowledge of all the people that have worked on this software artifact over the year. It will also learn from CI and CD faults, and it will basically take all this passive knowledge and make it active. And using that information, it will accelerate all stages of the software development lifecycle. So I know that it is quite abstract, so I'd like to make it at least one step more concrete by talking about specific tasks in the software development lifecycle and what Tabnine and others are doing there right now as we speak. Hopefully, you can see stuff from up there as well. I'll try to go over some of the things on this slide. The legend is that anything with a green dot is something that is being either worked on or already deployed. Anything with a purple dot is something that is slightly beyond the horizon, but not more than 18 months out. So let me just go over some of them. Again, just to get your imagination going. So some of the tasks that are already being actively deployed and used by users worldwide is obviously code generation for developers that I mentioned in the beginning. Just generating code in your IDE as you write code, fast forwarding you. Other things that are being worked on are test generation, code reading and navigation, helping you navigate and read a new code base as you enter it for the first time, accelerating new developers as they come in. Automatic refactoring, code review, automatic, both in the IDE and in the merge request and pull request. And again, this is, I know you're a varied audience, so please, again, if something is not clear, just ask questions. I'm happy to answer at any point. So let me just go through, maybe this will be too small on this projector, but we'll try. So again, no way you can see that. But hopefully, maybe the people, I cannot see it myself. There is something being typed there, okay? So this is just an IDE with Tabnine installed. What was written at the top is a comment text that says something like, I don't remember, create a student class, something, something, just a description in natural language of 2 lines that said, I remember actually, create a student class with first name, last name, and password, and then encrypt the password using SHA-256. And from this documentation, from this 2-line of natural language description, Tabnine generated the entire code block that is shown here, which I did not count the lines, but it's quite a lot. And from this, you can get a sense of why Tabnine automates 30% of the code that you write, because for many of the boring things, the repetitive things, the things that you don't want to write and have been written many, many times before, Tabnine can generate those automatically. Yes, please. Sure, so again, I ask for it in the comment, right? So I ask for SHA-256, I can ask for something else. So as usual in these cases, AI is a tool, and a fool with a tool is still a fool, right? So it's up to you to use the tool correctly. If you ask for SHA-256, you can only blame yourself. More to your point, this kind of violation or something that is not up to standard will be detected during code review, maybe by the same system, but now in detection mode that says something is not right here, and this is not how you encrypt passwords, right? But again, this is my fault here. Point was that from very short description, you can get the code completely automatically generated for you. And of course, it is still you, the human. You are in the driver's seat. It's up to you to make sure that the code does what you want it to do, right? The natural language description is a partial specification at the end. Any other questions here? Yeah.
You said this can help us automate the boring stuff.
Yeah.
How close are we to automating the interesting stuff?
So I think for the interesting stuff, the problem is to describe what is it that you want. The boring stuff, one of the characteristics of boring stuff that it is very compactly described, right? Create a student class with first name is something easy. Develop a new algorithm for matrix multiplication with complexity something is maybe something too hard. Any other questions? I think we can automate some of the interesting parts. Maybe a better answer to your question is that the bottleneck is the specification. So I would say almost tongue-in-cheek, we can already synthesize anything that we can specify, right? So that's roughly, it's not completely correct, but it's not very far. All right, other questions? All right, so let me just go to the next slide. All right, this is another simple example. There's a piece of code here that does find max on an array. And in this case, what I would like to do is I would like to automatically generate a unit test for this piece of code. So I can just go and click generate test there. And in this case, again, Tabnine will completely automatically, hopefully it happened already on your screen, there's a delay here, generate a unit test. Again, it's not the most inspiring unit test for checking that you got the max element of the array, but it is a useful scaffold or useful initial case from which you can develop further, and this will just generated right in less than a second. I just clicked a button and I got unit test, and I can get many more and get additional coverage, et cetera, et cetera. And of course, there are many, many other applications, ChatGPT that you've probably heard of, but there's actually an explosion of generative AI companies, products, startups in various domains. So there's stuff in text generation that helps you write text, stuff in image generation, stuff in code generation, including Tabnine here, and speech, 3D images, and any domain basically has a bunch of companies who are working on doing generative AI for solving tasks in this domain. And all these applications are powered by large language models, call them LLMs for short during the talk. And these LLMs are basically transformer-based models. If you don't know what transformers are, I'll explain that in a few minutes, at least in hand-waving fashion. And maybe intuitively what you need to know is that these are models that reason about sequences. They don't care a sequence of what is it. Actually, technically, they reason about sequences of tokens, so just integers as far as they're concerned. The models reason about sequences, and what they're able to do, they're able to capture relationships between elements in the sequence, and pretty sophisticated relationships, and they do that using a mechanism called attention mechanism, which again, we'll dive into the technical details of that in a few minutes. Interestingly, in LLMs, one of the things that is happening and is surprising and maybe even scary is that we are seeing what is called emergent abilities that present themselves as the models grow. So when you start with a model of, let's say, I don't know what we had a few years back, like 300 million parameters, small model, it can do certain tasks, it can do certain things, but once you start increasing the number of parameters to 10 billion, 175 billion, and beyond, the models start to be very, very good in various tasks that they were not even trained on. So they start to show emergent, oh, is that too strong or too weak? No, I know. They start to exhibit emergent abilities that do not exist in smaller models. So what I mean by that is if you look at a bunch of tasks, let's say truthful QA, which is the ability to answer its question answering in a truthful manner without being biased, like the kind of bias that you find in random human knowledge, like small amounts of human knowledge, then you can see the x-axis here is the number of parameters, and the y-axis is the accuracy of the model. And what you can see is that the model is doing very poorly. Sorry, the dashed line everywhere is random. So you can see up to like 10 billion parameters, the models are basically, for truthful QA, the model is basically as good as random up to 10 billion. But suddenly, once you reach 10 billion parameters, you see this green line here. Suddenly, it starts to become better and better as you add more parameters. Okay, so, and if you look at all of these graphs together, ignore for a second even what these tasks mean. You see here 8 different tasks, and you see that the models are doing relatively poorly, but at some point they hit a number of parameters, and suddenly, they become much, much better, right? And so there's a point for each one of these tasks in which you throw enough parameters at the problem, and somehow the model is good enough to deal with it. So for me as a human, this is quite scary, because it kind of raises the question, is quality just bred by quantity, right? Can we get human intelligence basically by just throwing more and more parameters? So if here we have like 10 billion parameters, what happens when we have 10 trillion parameters? What happens when we have order of magnitudes more parameters? What other tasks the model will start handling without us doing anything particularly special? And just to give you like a rough idea of where we stand on model sizes, the size of the circle here is roughly the number of parameters in the model. So you can see that in the old days, and old in kind of language model years, like something from 2008, 2018 or something is like ancient history. These are tiny models. 5 years is like, it's like different universe completely. And now, or GPT-2, that was 2019, it was a great model, 1.5 billion. This is tiny model compared to the kind of models that we have right now. For example, GPT-3 here, which is very useful, is 175 billion. But we're already getting models from Google, which are 540 billion parameters, 530 billion parameters, etc. So the number of parameters is exploding. And the number of models is exploding. Almost every provider here, there are models in this slide from Google, from, I guess, Meta, from, I know, open source models, etc. So there are many, many models, language models, LLMs. They are all based on the transformer architecture, and there are minor variants of them, like they vary a little bit in the architecture, but mostly it is basic transformer architecture where we just change the number of parameters. So all of these different circles are kind of the same basic architecture, not much innovation in the architecture itself. So I came here to talk about research in LLMs, not just about Tabnine and what we do. And again, all the images in my presentation are generated automatically. So it's a talk about generative AI. So all these images, they look strange because I just generated them from very simple prompts saying something like training a language model, horse jumping through hoop with fire or something like that. And so this is what you get. All right, so there are basically three rough categories of research in LLMs. There's the scalable training and inference, which is how do you take these models of 540 billion parameters, train them, you need tons of data, how do you serve them, typically multiple GPU instances, a lot of kind of engineering, hardcore distributed computation problems, synchronizing inference across multiple machines, moving tons of data. It's very interesting, but this is on the left-hand side. This is hardcore engineering. So I call it research, but because there is some research there, but it's mostly research not in ML, but actually in distributed systems and systems programming. Then there's the research in using language models. How do we take all this richness of models that I showed on the previous slide and use them for our applications? What can they do? What we can do with them? How do we do that? So this is more researchy. And then I guess the third category, which I also spend a lot of my time in, is the question of how do we understand these LLMs? Like they do all these emergent abilities, they do all these crazy things like generate code for us, generate text, generate images, but what do we know about how they work? What do we know? Do we have like a computational model that explains what is doable, what is not doable, how many layers of transformers do we need to accomplish some task? All these kind of more fundamental questions are stuff that is very interesting to me. So if you look at this kind of at a high level, this slide goes left to right from engineering to research, and some of this is really fundamental research that I'm not showing on the slide. Off the top, I think it's not the right thing for this talk, but talk to me afterwards if you're interested. Maybe another high-level point before I go into more details is in order to get the next generation of models, you need to do work here. Like just using what people are throwing at you from Facebook or from Meta or from Google or other places, that will not get you the breakthrough. This is just brute forcing science by increasing model size, brute forcing science and prefetching the future using prohibitive amount of resources. If you want to make the next qualitative jump, you probably also need to get better understanding of how these things actually operate. So exactly to this point, I have the next slide, which is the training compute in petaflops for training the models over the kind of the last couple of years. And if you can see this purple line with the problematic lighting in this room, you will see that we are reaching something like, what is it? I don't know, hundreds of millions or billions of petaflops required to train the models. I don't want to complicate kind of the definition of what exactly this means in terms of computation, so I'll simplify it for you. This is millions and millions of dollars. So to play in this game, you better show up with a check of $10 to $20 million in your pocket, Otherwise, just don't show up. Okay, so this is the game, and this is why all the big companies are very powerful in this kind of game of training models. And okay, I'll stop here, but again, it's a game for the big players. It's not a game for researchers who are trying to do innovative things. You just don't have the resources for this game. So I'm putting aside training and inference. If you'd like, talk to me afterwards, but I'd like to move immediately to the second category. And the second category is using LLMs as a black box. And what this means is that you pick a model from the shelf, from this huge slide of models that I showed you. Pick your favorite, the one that will actually fit in your GPU's memory, which may not be that many models. And now you can start using it. And the way that you use it is these models, as I said, they operate on sequences. So you give the model an input sequence, you get out an output sequence. Can be very quick, very fast, actually. In reality, it doesn't work like that. So you cannot just throw a sequence in the model and hope for something good to come out. You need to do some stuff in pre-processing and some stuff in post-processing. So there's probably some work around the model. For example, if you've heard the term prompt engineering, you need to kind of change what you feed to the model such that the model behaves properly for the input that you would like to get. And there's typically, you generate more than one output sequence, and then you need to do some scoring or need to do some other stuff that lets you pick between the different results that you get. When we generate code, for example, we let the model generate code as a sequence. Again, the model doesn't know anything. The model just operates on sequences. In code, for example, it operates on sequences of tokens, which means 2 to 4 characters. So it just generates basically a string of token. And because we want the code to at least parse or maybe compile, we typically have some semantic filtering that is done using a parser or using some partial compiler at the output of the model. Okay, so maybe my higher level point without the details here is that you pick a model off the shelf. You need to think a little bit about what to do in the pre-processing. You need to think a little bit about what to do in the post-processing. But basically, once you've done that, you throw a sequence in, get a sequence out. And again, images, for that matter, are also sequences of bytes, right? So the models operate the same, whether it is text, image, sound, audio, video, they don't care. For these models, it's just a sequence of tokens, and the model is able to uncover relationships between elements in that sequence. This is what these models do. Okay, so let's do a few examples. For example, we can take a model. In this case, I took GPT-3, and I gave it the question, the fastest mammal is, and GPT-3 came back and said the cheetah, which can reach speeds of up to 75 miles per hour, and even translated it to me to kilometers per hour, which was nice. I liked it. That was kind. So we started with this. Let's try a few more sequences just for fun. So I tried, when I showed these examples, the black part is the prompt, is what I wrote, the input sequence, and the green part is the output of the model. That's the output sequence. Again, remember, the model doesn't know anything about anything. For the model, these are sequences of integers, right? So just gets a sequence, outputs a sequence. So I ask, a brown horse is likely to run faster than, and then the model generated a white horse. Brown horses typically have higher levels of muscle mass and energy capacity, which means they can reach higher speeds than white horses. Now, I'm a very little expert on horses. So actually, to be honest, I have absolutely no idea if this is correct or not. Maybe someone here knows something about horses. But again, to your point, your earlier point, this is an output of a model. If I really care about it, I need to validate it. I cannot trust that the model generated something sensible, even when the model does that in huge confidence. So I tried something that is easier for me to at least check, like the Prime Minister of Bulgaria is. Oh, maybe it's not that easy to check, actually, right? So changes too frequently. All right, so, and indeed, I think this is incorrect, but you can, because the model has only seen data until 2021. And then I tried, the favorite food of the president of Bulgaria is, and so I have no idea what that is. And you can tell me if this is correct or not, but I absolutely have no idea. But this is what the model knows about presidents and Bulgarian food. And so maybe the point of this slide is that these models do much more than what you think they could, and also much less, in the sense of you can't really trust what is going on here, not really to the level. I think even a Google search that puts you on a random site will probably do better than a lot of this generated information. And I did not play any tricks. Like, these are the results straight from the model. I did not try to fail it on purpose. So let's continue with LLMs. I think it's more interesting just than asking general knowledge questions, which are clearly something the model can hallucinate with huge confidence. We can ask factual mathematical questions like the following, and maybe someone can answer from the audience what is the y coordinate of the point. I'll let you, while I drink, I'll let you answer. I think there are enough smart people here to solve linear equation. Sure.
I would like to ask, when you book ChatGPT, for example, if you ask a question that it doesn't have answer to, what happens?
Oh, the model always answers. There's no... In ChatGPT, there's a wrapper. Like, if you remember what I showed earlier here. This, like, so here. Basically, ChatGPT, the product, is not just a model. It has a post-processing phase, and then it can decide if the confidence is very low, and it has some other bias filters and nonsense filters and toxicity filters to make sure that it doesn't generate insulting stuff. And all of that happens in kind of the post-processing phase, which by itself, maybe my picture doesn't do like justice to post-processing. This is a very important and complicated kind of phase. The model is actually the small part. Most of the startups that I showed in the picture earlier are doing only this, right? They take model and they just do a lot of if then else in this part, or use another model to do the post-processing such that the product experience is sensible. Okay, so maybe ChatGPT, the product, will not output an answer due to the filters, but the model, you give it a sequence, you get a sequence. That's the game. Okay. So now you had even more time to think about my math problem, so hopefully somebody knows the answer. You told me this is a good university, Martin. Okay, okay, so let's ask the model if nobody knows linear equations. The model says the y coordinate of the point where this line crosses the y-axis is 0, which is incorrect. Okay, the actual answer is -10, if I remember correctly. And so we are sad and not surprised at all. So what people have done to kind of solve this problem is using something that is called few-shot prompting, which is quite a powerful idea. If you're not familiar with it, I think it's a good opportunity to get familiar with it. The idea is that we take the model and we show the model a few examples to help the model reach the right conclusion. So this doesn't require retraining the model. We're not changing anything in the model parameters. Just in the prompt that we're giving the model, we're feeding the model with additional information that will help the model reach the right conclusion. And this has been done very successfully in a lot of domains. I mentioned the papers here for those who are interested. So this has been done for common sense reasoning to improve how the model does common sense. It has done in mathematical reasoning, has been done also in symbolic reasoning, helping the model reasoning symbolically about certain domains. I'll show you a quick example with a very small font. The quick example with a very small font is mathematical reasoning. And I just want to go back to the linear equation that we had and help the model solve it. Okay, how do I help the model solve it? I take the prompt, the input to the model, and I just paste into the prompt this huge text of math problems that basically has the format problem, find the domain of the expression, blah, 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 solution, the expression inside root must be blah, 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 blah. And it even uses, like, if you are familiar, kind of LaTeX notation for the math symbols. And the model out, and I give the model the example, and at the end of the example, blah, blah, note that I give the model the example, at the end I write the courtesy text, I hope this is correct. So I gave the model one example, I gave the model a second example here, and again, I hope this is correct. And again, third example, and I end it by I hope this is correct. So I feed the model with these examples, okay? And at the end, so I take all these examples that I just showed you, including the solution, and then at the end, I paste my problem in the same format, which is this, a line parallel to blah, 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 the same problem that we had before. And now the model generates this. Since the line is parallel to this, and the equation is this, and the constant is this, and kind of walks through the reasoning, and gives me the final answer is -10, and you see the signature move of I hope it is correct. Why? Because all the example I showed the model had the same structure, and so I helped the model kind of verbalize the thinking process. Because the model has been trained on text, it verbalizes kind of what it learned is kind of how to verbalize thoughts, so to speak. I helped it understand that what I want from the model is kind of explained step by step in LaTeX, no less, if you see the kind of the notation, how to solve this problem, and I get to the right solution. Okay, so this is a very kind of simple and nice trick. We can do some other things here. I'll try to keep it simple. Seeing that you did not solve the linear equation, guys. Here's another chance. Math word problems. Again, Roger has 5 tennis balls, buys 2 more cans. Each can has 3 tennis balls. How many tennis balls? 11. So I have an example in my prompt, right? Now I give the second question. Cafeteria had 23 apples. They used 20 to make lunch and bought 6 more. How many apples do they have? And the answer is? No, 29. How do you, so the answer is not 29 here. 9 is correct. So the model is again incorrect. And what can we do to help the model? So again, we are sad. And we can do something that is called chain of thought. That is quite similar. It's a very fancy name to something that is really super simple. It's the same idea that I showed with the mathematical notation in the prompt, but now I kind of, again, force the model by example to provide more details. So instead of giving the example of Roger and the tennis balls, in the answer I actually say Roger started with 5 balls, blah, 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 blah. 5 plus 6 equals 11. The answer is 11. So I walk the model through the reasoning steps in my prompt. I give it the chain of thought that leads it to the right decision. And now the model, everything I show on my slides, by the way, I just don't do it online with the model because it's too risky, but it's directly copied from the model. Okay, so the cafeteria started. So you see, it follows kind of the same structure and reaches the correct answer. So again, I helped the model verbalize the thoughts and reach the right conclusion. Any questions so far? Yeah.
Superstructure, and with these prompts you're trying to navigate it into some narrow area?
Yeah, I think, well, nobody really knows, let's be honest, okay? But yeah, that's kind of the intuitive hypothesis, that you are structuring it to go to both the right area of the model, so to speak, and also to follow the right structure in that area. Does that make sense? It's, yeah.
And a quick follow-up question, if you teach it the wrong things,
yeah.
Does it know how to, I mean, it has some initial states that has learned some truth.
Mm-hmm.
And if I'm teaching it with these prompts the wrong things, is it going to start rejecting them at some point?
Yeah, it's a very good question, and people have shown that with not a lot of effort, you can make it do whatever you want. Yeah, so you can teach it that 2 + 2 = 5, and then proceed with that axiom to further reasoning.
So it's fairly flexible.
Yeah, it's very, very flexible. I'm going to show one last example of this because I want to reach the other part of my talk. So chain of thought is not enough, actually. And the reason is I will not bore you with the entire problem here. The reason is that once you have not just addition, but a more complicated structure for the computation, for example, in this case, the bakery bakes 200 loaves of bread and then sold 93 and 39 in the afternoon, but then somebody gave back 6 unsold loaves. So there's both addition and subtraction. The model gets confused. It doesn't know how to do both addition and subtraction and kind of does the wrong math and reaches the wrong conclusion. So, and again, I gave it the full chain of thought, right? I gave like the same thing that we did with the tennis balls. I walked it through the entire reasoning, but this was not enough. And so the problem, yeah, the chain of thought was not expressive enough to capture the structure of the desired computation. So do you have any idea for me what I can do? Sorry? Sorry?
How do you train the model with multiple ways of thinking with one assignment?
So yeah, so there is no training involved in anything that I showed, okay? There's just inference. I'm just like giving it a prompt, and it does inference of this prompt. I think what you're asking is, can I give it a prompt that does both chain of thought and something else in the same kind of prompt, or no? Maybe, okay, maybe you ask something else, then I don't understand, so.
For example, for the math problem, I have one way of thinking solving problems.
Yeah.
The person next to me has another way.
I see, okay.
And we want to use one sign-in.
Yeah.
And then, how do we do this?
Okay, that's a good question. I don't know if you heard that, like if we have 2 different ways to solve the problems and we want to offer both of them to the model, so the answer is that we add it to the prompt. In English, we say, here's one solution to the problem, here's another solution to the problem, and we hope really, really hard, because we don't understand any of this, right? So we really hope really hard that the model picks that up, and I think it would work. We can try it after the talk. Okay? But now I want to give you an idea that is very flexible and I think powerful, which is called PAL, or Program Assisted or Aided Language Models, which is done by my former student Uri Alon. And the idea is just like we did chain of thought, it's very, very easy to train a model to actually generate code instead of generate the answer, generate code that computes the answer. So instead of trying to force the model to do the complicated symbolic computation that reaches the right conclusion, we teach the model to generate a program that when this program will be executed, it will output the right solution for us. So in this case, the model just generates this program, which you see does the right assignment of numbers and the right equation with addition and subtraction that tells us how many loaves of bread you need. And really, what happens here is that we taught the model how to offload the symbolic computation to a different tool. Because we say, hey model, symbolic computation is hard for you, but very, very easy for another tool. Why don't you offload this to the other tool that is very useful? And a program by generated code, you can get very complicated chains of thoughts, so to speak. So people also call it programs of thought that are just richer than chains, right? Because you can have ifs, you can have all sorts of more complicated computational structures. Yes?
Is this done because it's easier to scrape data which has computational problems with code rather than word questions which have computational problems within them?
No, I think, well, part of it is because the model has been trained also on code, and the code provides the grounding of the structured thinking, so to speak. but part of it is really that the code provides the flexibility to get all the chains of thought or all the structures of thinking that you would like to get. And again, let me zoom through to the next thing, which is the kind of the next evolution, which is a recent paper from Meta called it the tool former. And tool former is kind of a generalization of what I showed with generating code. What tool former does, I hope you can see it in the back. Inside this is a trained model. It is trained differently, and it is trained to use tools. So as part of what it is generating, it is trained, for example, the purple thing here is calling a QA API, saying the question was, the New England Journal of Medicine is a registered trademark of, and because you know that this is a hard thing for the model to know, similar to who is the Prime Minister of Bulgaria, right? You just teach the model that it should ask something else. In this case, a QA engine, like what is the answer, and the model will just call the API of the QA engine. Same thing, you can fire a calculator, or you can fire some translation engine, or actually wiki search or Google search or whatever, that to help the model get the recent knowledge, the current knowledge, etc. So this is just the next evolution of using this. But maybe the conclusion for all of this, maybe what I want you to take from this section, even if you did not understand the details, is that using these language models as black box is very brittle, is something that is effective for many tasks, but sometimes gets things wrong. And actually, the worst part is that we don't know when it will get things wrong. We have no idea. It's not like the model really outputs a confidence score that we can trust that says, yes, if the confidence is low, we should not listen to the model. Sometimes the model talks nonsense with huge confidence, right? So this is a problem for the user. And even worse than that, results may vary drastically when you make minor changes to the input. Like it's enough in my examples to add an extra space or add a comma in the text, and the model reaches a completely different conclusion, right? So it's very, very brittle and hard. And as I mentioned earlier, many fundamental questions are open. Like, do we know what size of a model we should use to solve a task? Do we know how many transformer layers we need to do addition? Do we have a computational models that will tell us, that will be able to predict if something is doable with transformer or not? And this is what I want to talk about in the last part of my talk, which is understanding the LLMs. And really, you know, what I did seemed like magic, right? It generated all these answers and code and programs and chain of thought, and kind of it was really not understandable what's going on. And this just means that we don't have the science to reason about it. So let's try and build this science. And so if you give me a transformer and ask it like x plus 5 equals 11, what is it? That's a prompt. And transformer says x equals 6. It's a very, very simple question, like how does transformer compute this result? Transformer is a neural architecture. It has some structure. Can we understand how this result is being computed? It sounds very simple, right? Yeah, very frustrating. And so the idea that we had like a few years back, and it's really actually a whole research area now, is to use formal languages as a lens for investigating neural networks and expressiveness. So we started with recurrent neural networks, which are slightly simpler than transformers. They have a structure of taking steps. And we showed some results on expressiveness and provided basically a computational model for recurrent neural networks, also known as RNNs. And we also showed some results using formal languages on graph neural networks, showing all sorts of fundamental things that turned out to be in complete contrast to the title of the papers in which they were introduced. For example, we showed that something called graph attention network actually don't do attention. So once you start to read these papers carefully and analyze them theoretically, you get into quite surprising results. Back in 2018, this is just something that is easy to explain, so I showed it here. GRU is one architecture of recurrent neural network. LSTM is another. There's a plethora of many, many other recurrent neural networks, like cottage industry, at least there was, of different recurrent neural network models, and they were all considered to be equal to one another, but turns out, as we showed back in the day, is using formal languages that the architecture called GRU cannot actually count. And the way that we did that intuitively is we took a formal language like AN, BN, meaning equal number of A's and B's, right? This is like a formal language, and tried to teach a recurrent neural network to identify, to detect this language, to detect whether a string is in the language or not, okay? And what you see in these kind of graphs here is the hidden state of the network. Each color is different dimension. And again, if you don't understand what I'm saying, the important part is that in this picture, when you use an architecture called LSTM, you can see that one of the dimension is doing counting. So it is counting the number of A's up to a point, and then decrementing the number of B's, and it is able to accept the language or the word when the number is equal. So you can really see the network learning to count. And you can actually do it for more complicated languages like AN, BN, CN. You can see two counters, counting the A's, counting decreasing B's, increasing B's, decreasing C's, and accepting this language. So this is what you get with LSTM. But if you look at what happens with GRUs, you get this mess, which clearly doesn't look like the network has learned to count. All right, so this is not a proof that it doesn't count, because it may be counting in very complicated ways that are not easily visible when you look at the dimensions, the hidden state. But the paper has a proof that actually it cannot count. Okay, so this was the intuition that led to the fact that it cannot count. All right, so that encouraged us. And then we showed basically, we and others have showed that recurrent neural networks have a computational model. The computational model is a finite state automata. You can show basically that if you give me a recurrent neural network, a trained network, I can take this network and build, I don't say an identical, a similar finite state automata that simulates the behavior of the network. And the intuition is, if you look at a recurrent neural network, it's a network that is composed of cells coming one after the other. At each point, the input to the cell is the current hidden state, which is shown like here, and the input token from the string. So again, it's something that works on a sequence. So there are input tokens. There's a hidden state after I process every token. There's an initial hidden state. And the way to think about it is, I start from a cell, I look at the input state, this is the state before, this is the input to the transition, I make the computation, and then I get the hidden state as the output. So again, this is like, if you remember something from automata theory, this is like looking at the state before, this is the current state, this is the letter that you are reading from the input, and as a result, so here I show it in the automata, and as a result, you make a transition to the next state. And this is very effective, so you can actually, in a second, you can actually do exactly what I showed, which is take an RNN that has been trained without any prior knowledge about this RNN and extract an automata that simulates it with high accuracy. Yes?
That was my question.
Okay. Okay. So this is a computational model, and further, just a second, I'll get to you. Further, you can prove certain things can be done and cannot be done by reasoning on the symbolic representation, meaning on the formal representation, the automata, and then say what is going to happen in RNN world, right? So what we are doing here is we're connecting two very different universes. We're connecting the universe of neural networks, which is probabilistic and continuous and magical, with the beautiful, trusted, rigorous, symbolic reasoning of formal languages. And we're trying to bridge these two. We don't always succeed, but when we succeed, beautiful things happen. Yeah.
Is there an assumption that the input space is finite for this?
Yeah, sure. There are a lot of assumptions. Again, I cannot go into all of the details, and There are a lot of complexity results here and assumptions about the floating point representations and many, many other things that you can look in the papers. But the basic connection holds. Like you can connect quite directly in a very expressive way RNNs to finite state automata. Yeah. I don't remember the numbers off the top of my head. It's a paper from 2018, so God knows, been a long time, 2019 maybe. But it's very high. It's like for the formal languages that we looked at, it's very high. Again, if you look at RNN that is a very big, and you get an automata with million states, does not necessarily tell you anything practically interesting more than the network itself. So the importance is not in the practicality of taking an RNN and compressing it to automata. The importance is in the theoretical reasoning and saying things like complexity classes of different neural architectures by the way that they can detect different formal languages, like context-free languages, and contextual languages, et cetera, different classes of languages. And there's a whole line of work on that. So let me skip a bit. Again, because we have a computational model, we can do all sorts of magical things. We can do extraction, and there are some different approaches to that. We can analyze the expressive power and show all sorts of theoretical results. So people in the literature said like, oh, if you're trying to learn something that requires counting, don't use GRUs. Why? Who said? But now there's a proof. Don't use GRUs because they cannot learn that, right? There's a theoretical result that says this doesn't work, cannot work. There's like a lower bound, right? And you can actually generalize this to stack RNNs. So once you understand the formal model and the limitations, you can take it back from the formal model and introduce new neural networks that have richer expressivity because you understand the bottleneck, you understand the limitation, and where does it catch you. And you can look later, I'll obviously share the slides. There are links to all of the papers here. I think it's really a beautiful body of work. But I think I came here to talk about transformers and solve the question, what is the computational model of transformers? Like, can we do the same trick for transformers? Can I extract some symbolic entity that represents what a transformer does? Can I reason about computational model? If you give me a trained transformer network, like you give me GPT-3, can I extract X entity, something? I don't know even what is a symbolic entity. Are we out of time? Too many people. We started late, guys. Too many people are looking at their watch. So either this is boring or we're at time. OK, so I'll try to kind of give you the gist of this before we have to break. So we tried for a long time to extract transformer to some symbolic representation. And then we realized we have no idea what that symbolic representation would be. So it's not automata. It's not push-down automata. It's nothing of that kind. This is something more complicated. So we tried to define a programming language that we can decompile a transformer to that programming language, and it didn't work at all. And then we kind of had the aha moment that said, wait, let's go the opposite way. Let's think like transformers. If I define a programming language that follows the structure of what transformer can and cannot do, if I follow exactly the computation steps that are present in the architecture, without talking about tensors and floating point and all sorts of low-level details, just the abstract structure of the computation symbolically, like the clean structure of the computation without the implementation details, how would that look? And we created a language called RASP, which is restricted access sequence processing. That was a couple of years back. And since then, this language got a nice simplified variant by Sasha Rush. I think he did a much better job with the syntax and a much better job explaining our paper than what we did. And he made it a very nice syntax called RASPi, which is purely in Python, this language. And actually, people from DeepMind picked up our language and wrote a compiler from this language directly to transformers. So this language, I will show you the intuition at least in the 2 minutes that I'll take from your time. what this language does, it captures the structure of computation transformer, and you can write the computation in a programming language and then generate a transformer network without any training. So training is not required. We directly generate the floating point weights in the matrices of the transformer from a high-level symbolic program. So you don't need to train anything if you can write the program, which is not that easy. So here's a simple program in RASP. And what this program, RASPi, and what this program does is, again, everything works on sequences. So it takes an input sequence and flips it. And the way this program works, it does only operations that are allowed in transformers. So if you're familiar with transformers, you will identify things like key and query and value here, which are the transformer matrices. Yes, okay, somebody said yes. So you will identify some of the components of the transformer, but you will see that this is quite a convoluted language. It's not really clear, like, why am I writing things this way? But really, without getting into too many details, you can look at the paper. What happens here is that every line in this program is basically a different transformer layer. And these are computations that have to happen sequentially, one after the other, as stacked transformer layers. And for example, what I can tell you from this program is that if you would like to do the flip operation using transformers, at least using this solution, you need at least 2 transformer layers. You cannot do it with less. Maybe you have a more creative solution and you will write a different program that can be done in 1 layer. But if your solution follows this structure, you will need 2 transformer layers to solve this problem. So again, RASPi, the main operation is sequence operation. It transforms sequence to sequence. Let me jump ahead a little bit. Let's see. I jumped ahead just to talk about the attention mechanism. So if you don't know anything about transformer, this is your 30-second crash course about transformers. So transformer architecture is basically stacked transformer layers. Transformer layer is a feed-forward network, meaning a fully connected layer, followed by attention. And attention is just something that looks at the cross between the sequence and itself and tries to assign some score to how each token relates to other tokens in the sequence. That's a very inaccurate, hand-wavy explanation of what transformer does, but it's good enough for this talk. And what you look at GPT-3, or when you say whatever other models, basically they're taking this kind of structure and just replicating it, stacking it, many transformer blocks, one on top of the other. For example, GPT-3 is 96 such blocks concatenated one after the other. The intuition is the deeper the network is, the more computation steps you have. So the more layers that you have in the transformer, the more computation steps you have. And this is why when we had this simple program for doing flip, it required 2 layers. And you can imagine that if I'm doing something that is much more complicated, I would need many more layers. For example, I will ask you the lower bound question, how many layers do I need to perform addition of 2 numbers? Obviously, you have no idea. I didn't know either. So the answer is 6, if I remember correctly. At least 6 layers. And you can prove that. You can write the RASPi program that does this computation of ed. It's actually very complicated. And I can show you some example at least. Martin, you will have to stop me when I'm going really over time. This is the code, the RASPi code for ed. And every blue word here, like a toy or split or something like that, is by itself a procedure in RASPi that may involve multi-layers of transformer by itself, okay? And these are defined in the previous slides that I did not show you. But by themselves, maybe, see if I have them. Okay, I'll skip that. By themselves, they're quite complicated. And again, maybe the intuition here is that every line takes a sequence and does something to the sequence and returns a sequence. And then the next layer operates on the same sequence. And so we're getting basically a functional program that transforms sequences on every step. The interesting thing, maybe a high-level point, even if you don't know anything about transformers, if you write the Rasp program, what it generates is kind of intuitively an attention map. It generates this matrix that kind of captures how the model is combining information in the sequence. So it has some structure to the combination. So this is the matrix as created by the Rasp program. And this is the matrix. Oh, you cannot see with the projector, I think. And the one with that I circled in green is the matrix that has been learned when you train the transformer to do this task. Okay, so you can train a transformer to do the task, or you can write a Rasp program to do the task. And if you look at these two matrices, I hope it is visible in the projector, you will see that they're very similar. Kind of the structure of where they put the attention. Again, you don't have to understand the full terminology, but just the shape of the matrix, how it looks at the sequence, is very similar. Okay, it's almost identical. And maybe it's more apparent here. This is what is generated from Rasp, from the program, and this is the trained transformer. So you can see kind of the same structure of the attention matrices in the trained transformer versus the Rasp program. What this means is that the transformer trained to solve the task basically followed the same recipe that we had in mind when we wrote the Rasp program. So if you trained the transformer to do flip, and you used our flip program, they basically reach the same solution using transformer weights in the matrices. Okay. Finally, as I mentioned earlier, people from DeepMind picked up Raspi, picked up the language, and built an honest-to-God compiler that can take Raspi programs and translate them to transformer weights, again, without training. The beautiful thing is that you are generating a transformer network that implements the symbolic computation without any training to do whatever task that you want. And they can take these programs and compile it down to transformer, and they have a beautiful paper that follows many of our more challenging tasks and show how to generate honest-to-God transformer networks for them. To summarize, I showed you really two things. One is how to use LLMs, which was kind of, just to summarize, we showed like chain of thought and program of thoughts and toolformer and things like that. And I showed that you can get a lot of leverage from using these models without understanding anything about how they operate. But this is very brittle, very risky. And while it will work for many practical applications, something is still fishy that is going on, right? It's something fishy is going on, both in the stability and the robustness of the model, and also in the resources that are required to train and to do the inference. This is very expensive stuff for the kind of behavior that we are getting. And the second part, I showed you kind of understanding LLMs and really using formal languages and the connection between formal language and a neural network to reason about neural networks in a more fundamental manner. Finally, I gave the talk, but this is the work of many, many talented students from my group, and there are many papers that, again, you can look at later. And most of the software that I mentioned is available as open source, including Raspi, the Raspi compiler, etc. So at this point, I think I will stop and open the floor for some questions. Yeah.